So here we are, vectors and kinematics coming together. Let's have a look at this. Okay, so we've got a particle moving from a point with a velocity, and it's got constant acceleration, keywords, and those keywords mean that we can use SUVAT, but SUVAT with vectors. So for part A, we're trying to find the distance from the origin to the particle after 7 seconds. So the first thing we need to do is find out what the displacement is from the initial point. So I'm going to call that S. The initial velocity is that, the acceleration is that, and time is 7. So I want the formula that hasn't got the velocity in it, and that's S equals ut plus half at squared. You notice that the bold type indicates those things which are vectors. So putting the values into the formula for S, I find that the displacement from the initial position is that, and so the position vector of the particle after 7 seconds, I'm going to call that R, is the initial position plus the displacement that has taken place in that 7 seconds. So that gives us a total of 12.5 I and 78 J. So the distance from the origin is the magnitude of this vector R. And that's Pythagoras gives us 79 meters. So that's part A. So now what we want to do is to find the speed and bearing of the particle after 3 seconds, taking the J direction as north. So for part B, it's SUVAT again. This time we're not interested in the displacement. We've got the initial velocity. I'm calling the final velocity V because we're trying to find the speed and the bearing, and we can find those by finding V. We've got the acceleration and the time. So we want the formula that hasn't got S in it. So that's this simple V equals U plus AT. So there's the numbers going into the formula, and that's what our velocity vector is after 3 seconds. So how do we find the speed and bearing from that velocity vector? Well, I've just drawn a little picture there from using the 2I plus 11J, and the bearing will be this angle theta here measured from north. Remember that north is the J direction, and the magnitude of that vector, the length of that vector, will be the speed. So the speed is the square root of 11 squared plus 2 squared, about 11.2 meters per second. And the bearing is 10.3 degrees. So that's part A and B both completed. Let's have a look at part C now. We've got to find the times when the particle is 5 meters from the origin. So for part C, we're going to look at the displacement vector again, and this time we're looking for the times when the so we're looking for an expression for the displacement at time t. So S equals ut plus a half a t squared. So that's my expression for the displacement from the initial point. So once again, the position vector of the particle is this initial position plus the displacement from the initial point. So that gives me my expression for the displacement for position vector of the particle at time t. So we're told that the magnitude of this vector is 5, which are the distance is 5 meters from the origin. So what we need to do is find the magnitude of this rather intimidating looking vector and make that equal to 5. So the magnitude of that vector is the square root of the I component squared plus the j component squared, and that equals 5. So the first thing I'm going to do is square both sides and then multiply the brackets out, grouping the like terms, and now I've got a quartic. Luckily my calculator and class whiz and graphical calculators can solve quartics, and we get 2 different times at which the particle is 5 meters from the origin. So there we are.